And let me start to introduce our next speaker. It's Professor Ebrahim Karimi from the physics department here at the university. I don't need to read it, but let me read it. So Ebrahim Karimi received his PhD degree from the University of Naples under the supervision of Enrico Santamato and Lorenzo Marucci. Following his PhD, he took a postdoctoral position first in Naples and then came to the University of Ottawa to take a postdoctoral position, well, with me. He was then appointed to a assistant professor position. He currently holds a Canada Research Chair in the field of structured light. He is the group leader of the Structured Quantum Optics group, and he's working on applications of structured quantum waves, of both massive particles and the photons, and looking for developments in the field of modern science. So, Ebrahim?
Good morning, everyone. So, first of all, I would like to thank Professor Boyd and Professor Kokum for this invitation. It's always a pleasure to be in Schawlow-Townes, and it's more exciting when you can give a talk. You have the opportunity to give a talk. So, as Professor Boyd mentioned, the research that I'm doing is working with structured quantum waves, and mainly massive, which till now we could do structuring of electrons, and the other side is massless particle, which is photon. So here in this talk, I'm only concentrating on photons because I want to have a nice story and explaining to you what's going on with structured quantum waves and specially structured photons and their application. So if you Google it, which usually is a little bit strange, if you Google it, you will find structured light is a device which can do the 3D tomographic of an object. But here I will introduce you what I mean by structured light. Structured light, you play with different degrees of freedom of photons, or let's say in the classical regime with light. So either you control the wave vector, or you can control the polarization of the light, or you can control the phase front of the light, or you can control the intensity distribution. And in my language, I will call it either the phase can be helical wave, which is infinite dimension if you translate it in quantum language, and unbounded. If you look at the polarization, polarization is bidimensional, can be left-handed or can be right-handed. If you look at the radial mode, which is how the distribution and intensity in the radial part is distributed, is again in finite dimension, but is a little bit strange. It's not a usual form of being, is not the form of orbital momentum. And if you want to learn more about this, I want to guide you to these two works, which I have done with Enrico, and one of them with Luis Sanchez Soto, Gerd Loix, and Bob Boyd. So, which is a theoretical perspective of how the radial mode is useful and how is the group theory dictating this. So, just briefly mentioning, as I say, that if you talk about the single photon regime, a polarization of the light can have left-handed or right-handed. It means it can carry plus h bar or minus h bar unit of orbital momentum along propagation direction. However, if you talk about orbital momentum, the way that you can control the phase front of the beam, so usually we are familiar with the way that the wavefront is planar. So in this case, the beam, the photon, if you call it, does not carry orbital momentum, or it carries orbital momentum of 0. If you twist it in such a way that it forms like a spiral, then depending on the number of the spiral that you have it per wavelength, then you will get orbital momentum. So it can give plus h bar, minus h bar, or 2h bar, or in general, LH bar in units of orbital momentum, in LH bar, so which L is an integer. And the good point is here, it does not look like a polarization is unbounded. It can change from minus, let's say, 100 or 200, which the record, I think, is 10,010 currently in the world. And if we look at the intensity of these beams, it look like having, I'm asking you this question, what is the time in the North Pole? If each of us, we have a certain time, if you go to the North Pole, in the North Pole, the time is singular because you are not assigned into any specific places. So here is the same story. The phase is well-defined. However, the phase is well-defined here. If you jump around or if you rotate around, the phase increasing by 2 pi. But if you go to the center, the center has a singularity. This is a singularity that usually we have it in a cylindrical coordinate. So as a consequence, there will be no light at the center of the beam. So this is the reason that we call these sort of beams donut beams. And a very nice example of this, which I think many speakers, they use it, is the pasta fusilli. And that was one of the reasons that I went to Italy, Bob. So, and last time in Capri, Miles, where's Miles? Yes, Miles says to me that also, until that time, I believed that only orbital momentum of 2 exists, +2, and Miles found an orbital momentum of -2 in Capri. And in Capri, they have the negative side. So, if I can create a wave, a single photon or coherent light, which is a coherent superposition of radial mode, certain azimuthal phase structure, a certain polarization structure, and you superimpose them together, you will create a very complicated beam, which if you look at the point by point, you will see certain intensity distribution. Point by point, you will see a certain polarization distribution as well. And I mean structured light or structured photon by creating these sort of beams. Okay? So usually what we are familiar with is certain intensity distribution, and polarization is usually uniform, is linear polarization or circular polarization, or let's say anti-diagonal polarization or elliptical polarization. So that is the research field that I'm working on. And the first thing is that, okay, fine. What is new about these beams? First of all, we have to define what is the property of these beams. And one of the properties that we talk about is polarization singularities. It's not look like a phase singularity, it's about polarization. So if we look at the polarization is bidimensional space. You can easily map it on a Poincaré sphere. So usually what we do, we say, we assign, it's up to you. You assign left-handed to be in the North Pole, right-handed to be on the South Pole. And on the equator, what you will get equal superposition of these two. And specifically in the equator, you will get a linear polarization, which is, if you rotate it, you will see that linear polarization is rotating from H to V and from anti-diagonal to diagonal. If you go to upper hemisphere or north hemisphere, you will get left-handed elliptical polarization. If you go to the south hemisphere, you will get right-handed elliptical polarization. With the elliptical polarization, orientation will rotate. However, if you look at the Stokes parameter, which you will see in the next slide, the left-handed and right-handed and linear polarization, they are singular. What I mean by singularity, it means that here, the major and minor axis of the polarization ellipse becomes indistinguishable. So you have no clue what is the major axis and what is the minor axis. So this is a singularity for me. Doesn't mean that the light doesn't exist. Light exists, but you lose a property. You don't know a property of the light. And if you go to linear polarization, which I clearly indicate here, you have no right to assign orientation. You have no right to say what is the direction of the electric field, because the direction of electric field can be in both directions, so it can oscillate upon the time. So here, the arrow is singular. We don't know what is the arrow. So if you translate in terms of Stokes parameters, for the first case, S1 and S2 Stokes parameters will be 0, and for the case of the third one will be a third parameter of the Stokes, which will be S3. So I can create a polarization topology which is super rich, and that's an example. So at the center you have circular polarization, so usually we call it C point, and around it, what you will get L lines, which is the line of linear polarization. So on this line, all of the polarization will be linear. So we call it L lines. And usually what you will get, that C point is embedded by L line. And upon propagation, these C points will make a C line, so it will be a line, and the L line becomes an L surface, which embeds the C point. Okay, fantastic. I defined my language for you, and now I'm asking you, what is going on, how can we create these beams? So in our laboratory, we have a technology which is liquid crystal technology. We can align polymer in a specific orientation and topological structures, and then, which is done by photoelimination. Then you can insert liquid crystal between them, and you can create any sort of beams that you want. For example, here, they create in-Scotia beam, which is this is the experimental result. If you want to compare, is a low resolution. Or you can create, for example, Airy beams, or you can create a very high topological charge orbiting momentum. So this is an example that you can create L equal to, I think, 200. You can count it. Okay, so with this technology, we can create any structured light in laboratory. So the first thing that comes to my mind is, after reading a couple of papers, was that can we look at different topologies for polarization? And the first thing was that, can we take the polarization topology that I mentioned in the previous slide, which was C point and L lines, and doing tight focusing? And if you do tight focusing, what is happening? And that was a collaboration with MPL, with Gerd Bloch's team. And we had this liquid crystal device, and we created the beam that we wanted. So that's an example of the beam that we created as a C point and also a line around it. And we do the tight focusing. And with the technique that my colleagues Peter Banzer invented and Gerd Bloch, they looked at different spots and different point in the focal spot, and they look at the polarization X, Y, and Z component of the polarization, and also they look at the relative phases between them. So what they did, what we call it three-dimensional polarization tomography. So if you do that, surprisingly, you will see that EX has this form, though the beam is cylindrical symmetry. EX has this form, and that's a phase pattern. EY has this form and has this pattern. And EZ, which is due to the tight focusing, you will create a longitudinal electric field, has this phase structure. And that's the theory, that's the experiment. If you take the label out, it's extremely difficult to find out which one is experiment, which one is theory. That shows the precision of Germans. So we point by point plotted the polarization ellipse. The first thing that we should know, that is true that polarization is an ellipse. Even if you focus it, it still will remain ellipse. It will not become ellipsoid. That's a big mistake, okay? You have EX, EY, and EZ, but as a consequence, what is happening, this field is just rotated, okay? The electric field is just rotated. So that will be the ellipse, polarization ellipses for different regions, and that dimension, I think, is about 100 nanometer. And point by point, we show what is going on with the polarization ellipse, and the blue arrows shows the electric field vector. So you will see the electric field vector is continuous, but what is happening, the polarization ellipse, it seems that it has a twist in the 3D space. If you just look at the polarization ellipse and major axis of the polarization ellipse, what you will see, it forms a Mobius strip. And that was surprising. Isaac Freund in 2005, he predicted that if you take two beams carrying different polarization and different orbiting momentum, if you let them interfere coherently, you will create Mobius with different twists. And of course, if you look at the calculation, it's a little bit similar, not exactly. So under the tight focusing, you create such topological structures. Was that the end? No. 2 years ago, one of my students, I asked him, and he says to me, Ebrahim, you like knot? So let's take polarization and try to make knots, different type of knots. So he created, using spatial light modulator and using holograms, he created different beams. As a consequence, he created a very rich topological structure for polarization, which has a C point here, another C point here, another C point here, and certain L lines. So he showed that if you take these and plot them, for example, if you can take this topology and that topology, if you plot them, what you will get half link, or you will get cinquefoil link. So if you look at the C points, upon propagation, they form a knot, or they form a link. And for example, that shows how he was so good in experimental skills. So he could also generate a trifoil knot, which this trifoil is only the place which you have a circular polarization. So what is happening, the circular polarization becomes linear polarization split out, and it becomes two circular polarization with left-handed and right-handed, and then they combine, they propagate upon the space, and they form a knot in three-dimensional space. So, and for the first time ever, we were able to create figure-8 knot, which sounds to be extremely easy. I can create it with a knot word for you, but it was extremely difficult in laboratory. I think Miles tried, right? And since we could have a real-time measurement, it makes the technique extremely easy, and we could have a feedback and changing the phase front in such a way that we could create a figure-8 knot. And for sure, this is extremely difficult to see if that forms a figure-8 knot or not. So we made a 3D print, and really we look at the form that it forms really a figure-8. However, if someone knows the topology, they know that only looking at the string is not the way to characterize the topology, but also you can look at the surface. So I want to give you an example. Those people, they play soccer or football, okay? You have a ball, and if you look at the ball, the surface of the ball is not filled with hexagonal shape. It's a combination of hexagonal and pentagon shape. Why it is so? Because of the Euler number. So Euler number of this sphere is 2. If you look at the corners, if you look at the edges, if you look at the surfaces, if you do a calculation which will be V minus E plus surface, which is face, these numbers should be 2. If you make any shapes which has the same Euler number, then you can fill the surface of the sphere. In this case, we look at the surface topology in such a case that you plot the co-phase for the polarization, for example, for plus pi, minus pi 2, or minus pi over 4, or 0 or pi over 4, and we look at the number of the holes that you create there, and we find that, yes, we have a technique that can characterize the very complex topological structures. And very recently, we just look at a little bit of the C points, and we look at the linear polarization, and we find a very interesting topology which has never been seen, which is frame knot. This is a protected knot. So what you have, if I want to tell you in a lay language, is a combination of a Mobius and a knot. Why this is important? You will see it in a couple of months. It will give you the possibility to do topological computations, quantum topological computations. So if I want to tell you, any time that this string is passing through the other one, you can change the color. So here will be, for example, red, that will be the blue, and that one will be green. So you can assign each one to be sigma x, sigma y, and sigma z. And you can look at the way that this product will evolve. So, fine. We satisfy our curiosity. We can create different topologies. What is the application of them? So as an application, I will briefly mention 2 recent works that we have done. So that they are on the direction of quantum communication. So in the world of quantum, the first thing that we know that there is no definite reality. The reality is under question mark. And if you want to look, you will see the Schrödinger's cat. everything has a limit. If you want to measure conjugate quantities, they are bounded by as uncertainty principle. So if you want to measure X and P, you have a limit. And moreover, there is no cloning. So in the world of quantum, you cannot copy data. So these three, they will give you the possibility that you can encode information and send information in a secure fashion. So I'm not talking about the basic of quantum key distribution. What you have, we have Alice, which sends a message to Bob, and this message has a classical channel and a quantum channel. In the classical channel, you can send whatever message you want, and in the quantum channel, you share only the key. So this is the technique that we call it QKD. So usually what they do, in our case, which is high-dimensional quantum key distribution, we have a basis, which we call it psi. It looks like momentum base. And you can choose these bases in such a way that you can encode information of, let's say, -3, -2, or 3. And the other base is x. So you have momentum and you have position. So it means that the position is a coherent superposition of the rest, or is a discrete Fourier transform of the rest. So what does it mean? That you cannot measure these two simultaneously. If you are in X, you can measure the information, you can get the information. If you are in P, you can get the information. But if you generate P and you are measuring X, you have uncertainty, okay? So we use this technique to encode information, and that's the experimental results. So Alice generates the state in X and P and sends to Bob. Bob does in X, get information correctly with 100% certainty. If does in P, gets the right information, but if Alice sends in X and Bob measures in P, has no information, and vice versa. Okay, so that's important that it should be in the right basis. And you can use this technique, you can send a secure message, and after encryption, you have completely random, but after the decryption, you can get the information. In this case, we use 7 dimension, and we had about 16% of error in our system due to detectors, SLM, and etc. But however, we increased the bit rate from 1 to 1.73. So that's good. And what we tried, we said, okay, let's verify if our system is secure. So the first thing that we did, we tried to do one of the very trivial attack to a system, which is cloning attack. But what we did optimal quantum cloning. So we had a machine, which Frederick Bochard, one of my PhD students, at that time he was a master student, he built up the machine. It's the optimal quantum cloning. You send a state, a quantum state, but as a consequence of eavesdropper, this quantum state becomes a density matrix. It's not anymore a state, it's not pure, it has some noises, and keeps one of the photon for herself and sends the other photon to Bob. And that's a machine's very simplified version of that. I don't want to talk about this. And then, as a consequence of presence of Eve in the system, what is happening? The certainty in detecting in the right base will drop down to optimal quantum cloning attack limit. So you will see that this diagonal side is not anymore very bright due to the error that Eve introduced. So it reduces to a limit which is about 63%. So if you send the encrypted message, which I didn't highlight here, it's more error here. If you look at the random patterns, it's including more error. And if Bob, assuming that the channel is secure, which is not secure anymore, start to recognize the pattern, it sees that it contains a lot of noises. So as a consequence of Eve, the bit error rate increases from 16% to 57%, and the bits per photon, which was 1.73, lowers to be 0.36. By the way, this is not a secure channel. So, and that's the comparison between the two sites. Why we did that, we want to show to the people that if you do the high dimensional QKD, if you do in the dimension 2, the cloning attack will give you 83% of fidelity. But if you go to higher dimension, the cloning attack will give you 0.62 or 62% fidelity. So going to higher dimension will give you the possibility to reveal the eavesdropper much easier. And also on the other side, it allows you, that is the threshold that you have it for having a secure message. The threshold, you will see that by dimensionality, the threshold goes down. So it means that going to higher dimension will allow you to handle more noises, not due to attack to the system. More noises than you may have it, systematic noises that you may have it in your setup. So we brought up, why I have that? I don't know. So it got a lot of attention, but one of them, which was so annoying, was this. So it was a message in South China Morning Post. They say that I don't think the Canadian machine can hack it. If it did, the world of physics would collapse, of course. And they say the mainland quantum physicists who didn't want to be named due to the sensitivity of the project. And I think all of us, we know who wrote this comment. Okay. We try to go outside and do real-life quantum communication. And I don't know why we did that. I'm asking this question because the laboratory is a fantastic place. I will tell you some stories at the end. So my students, they were great and they were really motivated. They brought the equipment and we had a lot of difficulties, with sending messages or aligning laser or two roofs. So we choose Desmarais, which is one of the main buildings in the University of Ottawa, and Thomson, which is a residence building. And we brought our equipment there, and we had a single photon source creating photon pairs in a non-degenerate case. So we modify one of the photon states with the use of the Q-plate, these liquid crystal devices. And we use the other photon just to look where the turbulence, when the turbulence will be minimized. And we send the two photons there, which one of them only had the right information, the other one uses only for the timing. And on the side, we keep the target, and we had the signal beam, and we try to look at the information. And this was, first of all, single photon, and then it was coupled to single mode optical fiber. Those experimentalists, they know that this is extremely, extremely difficult. And the distance was about 300 meters, and the height was about, I think, 30 meters, right? Yeah. So, and here we use four-dimensional. So you can use this one as logical basis of 1, 1, 1, 0, 0, 1, and 0, 0. So that is the high dimensionality use. So instead of sending, let's say, 2 photons, you send a 1 photon, which creates the same amount of information. And they try to do look at the projection matrix. And as a consequence, you will see that in the case of 2-dimensional space, you had 5% of bit error rate, and it was 0.43 bits per photon. If you go to 4-dimensional, the error was 11% due to the detectors and also the devices that we had. But if you look at the information, was increased. Right now, we built up a much longer distance with the help of NRC. And the sender is in NRC in Montreal Road. And from the roof of library, we are sending information to Colonel Bay at the University of Ottawa. So the distance is 5.4 kilometers. And right now, we are getting also adaptive optics, very, very fast adaptive optics to compensate for the turbulence. We just characterize the turbulence there. And hopefully, this year, 2019, we can get some preliminary results. And the last part will be underwater quantum communication, of course. So we say that, okay, we try free space. Is it completely different regime? And we say, okay, you can have a quantum communication for the use of communication between submarines, or let's say satellite submarines. And my students, they had the scheme of Alice and Bob, but the channel now is not anymore free space air, but is underwater. They brought the equipment outside to Fred's parents, so they had a very nice swimming pool. They brought all equipment there, and they start to align. And finally, they tried to do quantum communication between Alice and Azad. So the first thing that we see, which we did not see in the free space we see turbulence, which only tip-tilt. The beam was just deviated in left, right, or up and down. In this case, we see very strange effect. If we send these petal beams, which is a coherent superposition of orbiting member of 2 and -2, we saw this beam at the end. By the way, this is not the way that we did QKD. We did it with a single photon. And we saw this pattern. And you see clearly that it's not only tip tilt, but also it's astigmatism. So we try to look at the characterization of this technique. So for example, we look at the case when you send orbiting momentum of 2, and as a consequence of astigmatism, the orbiting momentum, the beam split out in 2 orbiting momentum of 1, and it propagates, and you see the dancing between them. If you send L equal to 3, you will see that it becomes 3 singularities. And we try to look at the Zernicke polynomial, which is a measure that tells you how the astigmatism is evolving in the system. So you see clearly that A4 and A6, they are in the order of A2 and A3. So they are in the order of tip tilt. So we try to do the crosstalk measurement in order to understand what is the dimensionality that we can use it, and we clearly understand that the maximum dimension that we can go is just 3 dimension. So we choose this 3 dimension, and we try to do QKD, first in the 2 dimension, and with different protocols, which is a 6 states, and finally we did it in dimension 3. So in the dimension 3 was 11.7% of error, and it was 0.3 bits per photon. And this summer, we went outside. They like to being outside. I don't know why, my students. So they went outside and they did experiment in the river of Ottawa. So they tried to do underwater QKD in the river. Due to a lot of small particles that we had in the water, we were not able to go for a longer distance than 5.5 meters. Right now, we are trying to do in an NRC facility, which we are aiming for about 80 meters. So hopefully that will be the distance. And for the future, we want to do it with a satellite. So we have a technique to compensate for the surface turbulence. So with this, I will conclude my talk. So the topology can be so rich, even for the light. So if you want, you can create Mobius, or you can create knots, or you can create frame knots. You can go and send more information if you use high dimensionality, this multiplexing. You can use it in free space, or you can use it in underwater. So I would like to thank my team. First, going with Fred. Fred did most of the work on QKD and also on the high-dimensional quantum cloning. Alicia, at that time, she was a bachelor student. She did a great job, and she was leading the free space QKD project. And she was so kind that she stayed with me, and she's doing the long distance. Robert Fickler, he was supervising. He was a postdoc in my team, and Bob. He was supervising the free space QKD. And right now, he's an assistant professor in Finland. Whom else? Oh, Felix. He did underwater QKD with the help of other people. And that's all, yes. And I should thank also University of Ottawa. They give me the possibility to perform this sort of experiment, the funding agencies. And also, I should thank all my collaborators. There are only few names here, but you can find most likely more than 25, 30% of these people just in audience. Bob, Miles, Paul Corkum, and Gerd, and other people, Luis, and thanks to all of them. So thank you very much. It was a team effort, and we are very happy that we can do this collaboration and we can continue this collaboration. Thank you very much. In time?
I wonder the maximum distance a photon can be traveled in free space while keeping the structure of its mode, if you don't have any adaptive optics.
I think the maximum distance I have seen was 124 or 28 kilometers in Canary Island. Was Anton Zeilinger team. I can turn your question in a different way. I can say, what is the maximum distance useful for doing QKD? Because we aim that QKD, if you want to do it in free space, will be used for satellite communication with satellite. Going in a horizon for about 5 kilometers, you have the same turbulence if you want to go with satellite. Because the density of the air will change. So 5 kilometers on the horizon will be equal to sending the information to satellite.
Concerning these knots, well, I understand you didn't use them in QKD. What do you want to do with them?
With what?
With knots.
Knots. Oh. That was an abstract mathematics, by the way. It was a collaboration with Mark Dennis. I didn't mention that, I apologize. So it's really an abstract mathematics and also understanding what is going on with the topology. I don't know. I don't know the real application. If I want to decompose it, it will be in dimension, if I'm not wrong, 24. So if you want to see it in this way, you can do high dimensional QKD in dimension of 24.
Must be difficult.
If you want.
There's something I didn't understand. Let's remember BB84, and in its normal implementation, there is a length, let's just attenuate. And beyond that length, one can make key, but it's not secure against an arbitrarily advanced Eve. So you gave key rates and error rates, but what's the maximum length if all we did was attenuation for which your protocols are secure? And then there are techniques like the, what are they called? The pulses that are injected, the decoy pulses to extend the length, but still there's a length at which you can no longer be secure. And I haven't understood your key rates and error rates in terms of finally there's a length you can't go any farther, and do you improve over the kind of Broussard, Bennett, and other like decoy?
Right. So if I understood your question, you say that, okay, in the BB84 protocol, the standard BB84 protocol, what you have a certain distance, which is security distance, you call it. So this security distance is defined based on the errors that you can enter to the system. So if you go to 100 kilometers, which I have a doubt about that, if still you have 5% of error, your link is secure. So the error dictates really if whether this length is secure or not. So that's all. So so for example, if I have
the error rate when yours becomes non-secure?
Pardon?
How does the length at which you can send your multi-alphabet key compare with the link I could do with BB84?
So you're asking about high-dimensional QKD and two-dimensional QKD. If you're asking about the two cases, in all cases we have errors. So if you have error of 11% in 1 meter, or in 100 meters, or in 1,000 meters, if you have 11% of error, you are not able to establish a key. So your link is unsecure. Maybe due to the length, you are introducing more noises, systematic way, but for us, any noises is coming from Eve. We don't know really that this error is coming from the channel, is coming from something else. So if you go with high dimensional, what you do, this threshold that you can have a cutoff, this threshold goes down. So what is happening? The threshold now becomes 25%. I think 25% is the optimal way. So you can, even in the channel which you have 100 meters, in two-dimensional case, you have 11% error. You cannot establish a QKD. You can go with 7 dimensions, but still in the same distance, you have 11%, which I adopt. It will be a little bit higher, but still you can have a established key. So the effect of the link will be only changing the errors.
Now, I have a comment regarding this discussion. So the attenuation in a fiber goes down exponentially,
Right.
and in a free space it's different. But despite of, so this attenuation will, in BB84, will take the key rate that you can get, take that down. So you could go on, and people have done this and pushing this.
Right.
And then at some point it breaks off, and I think this is what Jeff was referring to. And in BB84, this is typically the dark counts in the detector.
Right.
Had you better detectors, you could go further on. And if, so here it applies in a similar way, I think. If you
Right.
do it with single photons, and if you do it with continuous variables, then you still have electronic noise in the detector, which you can try to reduce, but this will also be the limit. So I think it's always this, ultimately the detector that will determine how far you can go.
Definitely. So essentially, I mean, I don't want to extend it in this way, but we characterize different protocols, different dimensionality, and we look at the different ways that you can implement QKD. And it turns out really that's a detector that dictates really what's going on. Because detectors, even if you go to high dimensions, what is happening, they click in a wrong way, then they introduce more noises. And of course, I mean, if you want to look at the long distance and you want to look at the way that how the distance will affect, by the way, this is not a fiber, this is a free space, everything is going linear. Underwater is a different story, it's going exponential, it's a Beer's law. But I would say the generation technique and detection technique, they really play a role. And optimal way with the current technology that we have is dimension 4. Really going to dimension 8, you will not gain anything. I mean, we have a manuscript on that, is on the archive and on the review, so I can send it to you. And also, I think Gerd is a co-author of that work as well. Yes.
Let's thank Professor Karimi.